For topic two, we're going to start talking about problem solving. This is kind of like an offshoot of that direct translation. Direct translation, we're just practicing, hey, converting words to math. Problem solving, you're starting to get into a situation where you maybe have more like a real world situation attached to the problem, okay? But please just know problem solving is yet another way us math teachers trick you into thinking, hey, we're going to be doing some math, but it's really just word problems, okay? So, word problems. Okay. So I would love to tell you there's just one set of steps that you can always use to solve word problems, but that just isn't so. Okay. So like when we're solving an equation that has fractions, I can say, hey, clear your fractions, get rid of parentheses, combine like terms on the left or right, apply the addition property of equality, and then wrap things up by applying the multiplication property of equality. And that's really always going to work. When it comes to word problems, there's not really one hard and fast rule because each word problem is going to be kind of different, okay? So we certainly have themes of word problems. We have types of word problems that are going to have a much more similar setup, but generally speaking, every word problem is going to be different in some way, shape, or form, okay? So you just have to kind of get to the point where you're sort of comfortable trying stuff, okay? And if you try something and it doesn't work out, try something new, okay? Now, steps used in problem solving. So here are some tips and tricks. They may not always, they're always going to work. It's just not necessarily quite the clear set of steps that we like in a math class, okay? So the first thing is understand the problem. And a lot of times that's the hard part is just understanding, okay, like what's happening in this word problem, okay? So it says start by reading the problem thoroughly to understand what is being asked. Just kind of acclimate to the problem, sort of familiarize yourself with the problem. Sometimes you have to read the problem two or three times just to kind of wrap your head around what they're saying, okay? Part of this is understanding what information is important and essential to the problem and what information is just kind of like filler, okay? Next, translate the problem. This is the direct translation part. So when it says translate the problem, that means to write the problem in short form using words and then assign variables. So for me, I'll take some time, I'll understand the problem, and then I'll translate the problem into just like a sentence with like just really basic words, and I'll show you what I mean in just a bit. And then I'll translate it into just an equation with just numbers and variables. Okay. And then from there, we just use the tips and tricks that we already know for solving the equations. So once you get through the first two steps, it's pretty easy from step three, just solving the equation. Okay. So perform the indicated operation. Estimation can be used to get an idea of what the actual solution might be. Now, for us, it's a bit more than just performing an indicated operation. For us, it's more like solve the actual equation. And then the last step you do have to be careful with, it says interpret the results. Okay. What this means is make sure you answer the question fully, make sure your answer makes sense in terms of that real world scenario. And then you always want to write out your result with like a very brief description. We don't want what I call naked numbers. Okay. If you just throw a number at me, it's like, cool. What does that number mean? You have to tell me what that number means in the context of that problem. I'm not looking for a paragraph. I'm looking for just a really brief description. Okay. And make sure, if necessary, you include units with your answer. So let's go ahead. Okay. So the first two parts of example three are very similar to what we just did in examples one and two. But then when we get to parts C and D, we have kind of that real world aspect. Okay. So example three says translate each scenario into an equation and solve. Okay. So for part A, we have 5 times a number. So we're going to take some unknown number. We don't know what it is yet. We're going to multiply it by 5, and then that is decreased by 3. Okay. So just off the bat, let's go ahead and assign our variable. Let's say let x, well, I forgot my x. We're going to let x equal the number. We don't know what the number is, but we're going to call it x. So right off the bat, I know I'm going to take 5 times whatever that number is. So that's just 5x. And then that's decreased by 3. So that just means subtract 3. And then that is equivalent to, that would be my equals. It is equivalent to the difference of twice a number and 18. So we want to subtract twice a number. So 2 times that same number. And then we want to subtract from that 18. So what we have is 5 times a number, x, decreased by 3 is equivalent to the difference, that just means subtract. And we've got the difference of 2 times a number, so 2x and then 18. All right, so now we have a pretty easy equation to solve. So this is what we want to solve. Okay, so the normal steps for solving an equation, we would get rid of parentheses if we had any. We don't have any. The second step is to simplify the left and the right-hand sides of the equation separately. We don't really need to do that. Both sides have just two terms, one variable, one constant. We can't combine on the left. We can't combine on the right, so we can jump down to step 3. Step 3 is where we apply the addition property of equality, okay? That is where you start moving things on both sides of the equals. So you move things from one side to the other. And you always, for me, I don't want to say you always, but you generally prioritize your variables. So you want to get your variables on one side, typically the left, doesn't have to be, but typically the left. And then we move our constants to the right, okay? So for me right now, I'm looking at this 2x on the right. I want to move it to the left. Since it is a positive 2x, we think of that as plus 2x. So how do we undo addition in math? Well, we subtract. So I want to subtract 2x from both sides of the equation. So on the left, 5x minus 2x is 3x. And then I can drop down minus 3 equals. And then on the right, 2x minus 2x is 0. And then 0 minus 18 is negative 18. Okay? So we got all the variables into a single term on one side of the equation. Now we want to do the same thing with the constants. We want to isolate the 3x term. So the issue is this minus 3. So in math, how would we undo subtraction? Well, we would add. So I want to add 3 to both sides. On the left, negative 3 plus 3 is just 0. And then 3x plus 0 is 3x. And then on the right, negative 18 plus 3 is negative 15. And then finally, I want to get my x alone, and I'm almost there. When you get to the point where you have a single variable term equaling a single constant term, that's when you apply the multiplication property of equality. So we want to undo the multiplication of 3 and x. So in math, how do we undo multiplication? Well, we divide. So we're going to divide both sides by 3. On the left, 3 divided by 3 is just 1, and then 1 times x is just x. I'm going to scoot it over here a little bit for the sake of room. And then on the right, negative 15 divided by 3 is negative 5. And because this is really just a regular old equation, you could write it fancy like this. Or because you started with a word problem, you could write your answer kind of in words. You could say the number is negative, is negative 5. All right, there you have it. So that is problem solving, okay? It certainly is nice when they just give you the equation and like, here it is, solve it. But sometimes they're gonna be like, here are a bunch of words that if you translate them just so, you get the equation we want you to solve. And that's what's happening in part A and part B. All right, for part B, we have that 80% of a number is added to the same number. So that's kind of tricky, but I'll show you, and it's going to make more sense, I think, in future examples. But 80% of a number is added to the same number, and the result is 252. Find the number. First of all, just really quick, in math, when we have percents, we write them as decimals, okay? So in math, percents equal decimals. Okay, so if you're given a percent that's like got the little percent symbol and you need to convert it to its decimal form, no big deal. To convert, move decimal to the left twice. Okay, so off to the side, let's kind of address this 80%. So we have 80%. We don't want to write it as 80% because in math, that 80% doesn't really work for us. We need it to be in a format that we can use, which would either be a fraction or a decimal. Decimals are just easier. Okay, so if you don't see a decimal point, you assume it's at the end of the decimal. So we would say it's over here. We would move it to the left twice. So 1, 2. That would give me 0.80 or just 0.8. You don't need that 0 at the end. And then you just drop the percent symbol off. Okay, we just don't need the percent symbol anymore. Okay, so that is how we would write 80% as a decimal. So 80% equals 0.8. Okay. Now what we want to do is we now want to assign our variables. So we're going to let x equal a number. We don't know what this unknown number is. We just know it's unknown. So we're going to let x equal the number. Okay. And now we want to translate and get some kind of equation. So we want 80% of a number. In math, a lot of times when you see something like 80% of a number, the word of really just means multiply. So if we're going to take 80% of a number, we're going to multiply this number by 80%. So that would be 0.8x. Okay. And then it says 80% of a number is added to the same number. So we just want to add x again. And then it says the result is 252. Okay. Now you might read it as x plus 0.8x. If you say that 80% of a number is added to the same number, you're going to get the same thing. Okay. These two equations mean exactly the same thing. If you wrote the top one or the bottom one, I'm going to be happy as can be. Okay. So now we just need to solve the equation, and this one's going to be pretty easy because we can definitely simplify on the left, okay? You have to remember that when you have just a plain old x, there's technically a 1 there, so that's really 1x. So 1x plus 0.8x is 1.8x, and then that equals 252. Okay. And then in order to solve this, we're good. We've got the single variable term on the left, the single constant term on the right. We have one step left and we're done. All we have to do is undo the multiplication of 1.8 and x. So I divide both sides by 1.8. On the left, 1.8 divided by itself is just 1. 1 times x is x. Remember, a lot of times we'll get lazy and we'll be like, oh, the 1.8s cancel. They sure do. Just know what that means. That means when we divided them, we got 1. Okay, and then 1 times x is just x. And then on the right, you can just get out a calculator if you don't have yours out yet. We take 252 divided by 1.8, and it's kind of getting dark in here. We get 140. And that's it. So in a situation like this, you can write it fancy in set notation. Oops, I forgot my one. Or because you started with a word problem, you could write it just as a really quick phrase or a quick sentence. You could say the number is 140. And that's it. Isn't it kind of fun? Like maybe secretly it's sort of exciting and fun. All right, so that's A and B. Those were just really generic statements. Now we're going to start looking at situations where maybe there's like a little bit of a story involved. So the last two parts of example 3, we have kind of like, I don't want to say an actual story. It's not like I'm going to be reading Hansel and Gretel to you, but there's like a real world aspect to it. Okay. So Part C, Jim and Pam, I can tell you right now when I was making this worksheet or the original word problem, I was for sure watching The Office, okay? Which I already know I'm 1,000 years old compared to everybody in this class, but I was watching The Office on this one, okay? So let's just read the problem a couple times. It says, Jim and Pam saved $56. Jim saved 8 more than Pam saved. How much did each person save? So imagine two kids, they're pooling their allowance, they're trying to save up for something, okay? And what we know when they pool their allowance combined, they saved $56, okay? Now, I will tell you, I have a very particular way that I solve problems like this. I have kind of a vertical setup. If you think of this horizontally, you could do a horizontal setup. I am absolutely fine with you doing these problems a little differently. However, here's the caveat. You must use algebra, okay? We can play around and use trial and error and eventually figure out how much each person saved. I'm not interested in that. This class isn't called quantitative trial and error, okay? It's called quantitative literacy, and part of this is understanding algebra. So I do insist that you use algebra. I want to see your equation and I want to see you solve the equation and then interpret those results, okay? So hear that loud and clear. If your work does not have algebra in it, I'm not going to feel overly compelled to give you credit, okay? So here's how I start this. We know that Jim and Pam were saving money. So I'm going to start with Jim plus Pam. So if Jim saves some money and then Pam saves some money, we know it added up to be $56. So if I take the amount Jim made, add it to the amount Pam saved, we have 56 bucks. Now we start doing the direct translation. And here's the tricky part. We have a goal. Our goal is to assign the variable to the unknown. At this point, we don't know how much Jim saved. We don't know how much Pam saved. So we kind of have two unknowns. But there's always going to be one thing that you know less about. Okay? So go back and look for a hint in the problem. As I'm reading this problem again, okay, Jim and Pam saved 56 bucks. We're pretty good there. It then says Jim saved $8 more than Pam saved. That tells me I know something about Jim. I know nothing about what Pam saved. So what we want to do is we want to assign the variable to Pam. So we're going to say, okay, Pam saved X dollars. Okay. Now use that to write an expression to represent how much Jim saved. So Jim saved 8 more than Pam. Well, if Pam saved X dollars, that means Jim saved X dollars plus 8 more. Okay, so algebraically speaking, Pam saved $8, Jim saved X plus $8. Okay, now because of this vertical setup, I can just combine each column here. Okay, if I add up Jim and Pam, I get 56. If I add up my X's, I get 2 X's. And then there's nothing to combine with that plus 8, so I just drop it down. And y'all, that is the equation that we need to solve. So when we solve this equation, when we solve this equation for X, we're going to figure out how much money Pam saved, and we'll use that to figure out how much money Jim saved. Okay, so in this case, I'm going to leave my variables on the left. It'll just save us a step, but at the end, I'll kind of make sure I write my answer X equals, just FYI. But I've got a single variable term. I'm going to leave it alone for now. I want to isolate it though. So I want to get that 2X alone. The issue is plus 8. So how would I undo plus 8? Well, whoops, I would subtract. So I'm going to subtract 8 from both sides. On the left, 56 minus 8 is what, 48? And then on the right, 8 minus 8 is just 0. So yes, we get lazy as mathematicians and we're like, oh, the 8's cancel, but please understand why we say they cancel. They cancel because they have a sum of 0. And then 2x plus 0 is just 2x. Okay, so we were able to kind of get that 2x alone. Now I need to get the x by itself. So I've isolated the variable term. Now I need to isolate the variable. So how would I undo the multiplication of 2 and x? Well, in math, we undo multiplication with division. So on the right, 2 divided by 2 is 1, which leaves me with just a single x. And this is where I flip my x to the left. And then 48 divided by 2 is 24. Please don't stop here. Don't stop here. All right. Yes, you have solved the equation, but you haven't interpreted the results. So we have to go back and kind of figure out, okay, what does X mean? Well, X was the amount of money that Pam saved. So Pam saved $24. Well, if Pam saved $24, Jim saved 24 plus $8. So what's 24 plus 8? That would be 32. And then let's just check this. This is kind of like our check column. All right. If Jim saved 32 and Pam saved 24, how much did they save together? Well, 2 plus 4 is 6. 3 plus 2 is 5. Hot dog, y'all. We were able to get it to check out to $56. So now we can say officially, Pam saved $24 and Jimothy saved $32. And that's it. Okay. So yes, I told you before, you can play around with your numbers and use trial and error and you can figure out the answer. But remember, the name of this class is not quantitative trial and error. The name of this class is quantitative literacy. And part of that is understanding basics of algebra. You must show me algebra. You must get an equation that you can then solve. Okay. So last up for this video, we have part D. It says a 12-foot board is cut into 2 pieces. The longer piece is 3.5 feet longer than the shorter piece. What is the length of each piece? I'm having a hard time talking tonight, y'all. Okay, so we can understand we have 12 feet of a board. So some board measures 12 feet long. We cut it into 2 pieces. Of those 2 pieces, we have the longer piece, and then we have the shorter piece. And if we were to glue those 2 pieces back together, what had they better measure up to? Well, they would have to have a measure of 12 feet. So if we take the length of the long board, add it to the length of the shorter board, they have to add up to 12 because that's what we started out with. Okay? Now is when we do the direct translation part. We kind of have an idea. We have two different boards. They're both separate lengths, but they started from one 12-foot board. So if we add the length of the longer board to the smaller board, must equal 12. Okay. Now we want to assign the variable. So we don't know the length of either board. So technically we have two unknowns, but we always want to go back to the problem and find a hint about one of the pieces. So there's going to be one piece that you know less about than the others. That's what gets the variable. So if we go back here again, 12-foot board cut into two pieces, we're good there. The longer piece is 3.5 feet longer than the shorter piece. That tells me I have a hint about the longer piece. That means I know less about the shorter piece. So I'm going to let the shorter piece be X feet. So of those 12 feet, X of them went to the shorter board. Okay. Now, because the longer board is 3.5 feet longer than the shorter piece, we know it's the length of the shorter piece plus 3.5. And that's it. So you now have an expression to represent the length of the shorter piece. You have an expression to represent the length of the longer piece. And if we add up these columns, we'll get an equation to solve. Okay, so short plus long is 12 feet. X plus X is 2X. And then there's nothing to combine with 3.5, so I just drop it down. And now we have an equation that we can solve. Okay, so again, I've got a single variable term. Let's isolate it. So the issue is plus 3.5. So how would I undo addition of 3.5? I would just subtract. So I'm going to subtract 3.5 from each side. On the left, 12 minus 3.5 is what, 8.5? And then on the right, 3.5 minus 3.5 is just 0. Again, we would say it cancels, but please understand why. It has a sum of 0. So 2x plus 0 is 2x. And then since we've isolated the variable term, now we want to isolate the variable itself. So we need to undo the multiplication of 2 and x. So I would divide both sides by 2. 2 divided by 2 on x is just 1. 1 times x is x. And then 8.5 divided by 2 is 4.25. You can certainly use your calculator there to check. And again, don't stop here. We have to interpret the results, okay? So if we go back to the original problem, let's make a little column to check our work. We know that the shorter board was 4.25 feet long, okay? We also know that the longer board was 3.5 feet longer than that. So we would take the longer board, we know it is 4.25 feet plus 3.5 feet, okay? So if we add that, we get what, 7.75 feet? And we want to add this up and make sure it adds up to what? I'm imagining you at home shouting 12, 12. Yes, these two pieces have to add up to 12. So let's see, 5 plus 5 is 10, keep a 0, carry a 1. 7 plus 1 plus 2 is 10, keep a 0, carry a 1. Drop down your decimals. 7 plus 4 plus 1 is 12. So everything checks out. So we could say the long piece was 7.75 feet, and the short piece was 4.5 feet. And that would be our final answer. So look, I'm not looking for like a paragraph description of what your answer is, but I am looking for you to describe the numbers in your answer, okay? So don't just solve the equation and think you're done. You have to interpret the results and answer the question completely. The question here says, what is the length of each piece? You have to state what is the length of each piece. In the previous example, the question said, how much did each person save? You have to state how much each person saved and label those answers very, very clearly. Okay, so that is kind of an introduction to problem solving. In the next videos, let's see, I can't remember which order I have them in. So next we're going to look at price increases and decreases, so percentages. We're then going to look at something called break-even problems and then solving a formula for a specific variable. So 3 more videos and we are done with 6.3.